Welcome to Universe Scientist Stories. Tonight, we are leaving the boundaries of the present day to embark on a slow, chronological journey through the vast scales of cosmic time. We will trace the history of our universe from its earliest moments, through the fading light of distant eras, and into the absolute stillness of the far future. Dim your screen, settle in, and let us drift through time. Our journey begins approximately 13.8 billion years ago, at the earliest moment for which modern physics can provide a meaningful description. The observable universe was once compressed into an extraordinarily hot, dense state. Temperatures exceeded trillions upon trillions of degrees. Matter as we know it could not exist. At these energies, the familiar distinctions between particles and radiation become less important than the underlying quantum fields that filled all of space. The entire observable cosmos occupied a volume vastly smaller than it does today, and every region was immersed in conditions unlike anything that can currently be recreated in laboratories on Earth. During the first tiny fraction of a second, the universe underwent a period known as cosmic inflation. In an extremely brief interval, space itself expanded at an extraordinary rate. This expansion was not motion through space, but rather the stretching of space itself. Distances between points increased exponentially. Regions that were once quantum scale became large enough to eventually contain galaxies, clusters of galaxies, and immense cosmic structures. Tiny quantum fluctuations were stretched across astronomical distances, leaving subtle density variations that would later guide the formation of every large structure in the universe. As inflation ended, the energy associated with this process was converted into a dense sea of particles and radiation. The universe entered a phase sometimes called reheating. Matter and antimatter particles appeared in enormous quantities. For reasons still not fully understood, a slight excess of matter existed over antimatter. The imbalance was remarkably small, perhaps only about one extra matter particle for every billion matter-antimatter pairs. Yet that tiny asymmetry determined the existence of all future stars, planets, galaxies, and observers. Had matter and antimatter been produced in exactly equal amounts, they would have annihilated almost completely, leaving a universe dominated by radiation alone. Within the first few seconds, the cosmos was filled with fundamental particles moving through an intensely hot environment. Quarks, electrons, neutrinos, photons, and other particles interacted constantly. Temperatures were so extreme that stable atomic nuclei could not yet form. The universe behaved as a dense plasma in which collisions occurred continuously. Even though the universe was expanding rapidly, it remained remarkably uniform on large scales. The seeds of future cosmic structures already existed, but they were still only slight variations in density hidden within an otherwise smooth cosmic environment. As the universe continued to expand, temperatures gradually fell. Roughly 1 second after the beginning, neutrinos ceased interacting frequently with other matter and began traveling freely through space. These nearly massless particles still fill the universe today. Trillions pass through every human body each second without notice. The cosmic neutrino background remains one of the oldest surviving relics from the early universe, although its direct detection remains an extraordinary experimental challenge because of the extremely low energies these particles possess after billions of years of cosmic expansion. A few minutes later, conditions became suitable for the first atomic nuclei to form. This period is known as Big Bang nucleosynthesis. Protons and neutrons combined to create hydrogen nuclei, helium nuclei, and trace amounts of lithium. The process lasted only a short time before expansion reduced temperatures too far for fusion to continue efficiently. The resulting composition was remarkably simple. About 75% of ordinary matter became hydrogen, while most of the remainder became helium. Only tiny traces of heavier elements existed. The carbon in living organisms, the oxygen in Earth's atmosphere, and the iron in planetary cores had not yet been created. For hundreds of thousands of years afterward, the universe remained opaque. Electrons moved freely through space, scattering photons in every direction. Light could not travel far before encountering another charged particle. Although the cosmos was filled with radiation, there was no clear view across large distances. The universe resembled a glowing fog of plasma. Every location was immersed in intense light, yet no observer could have seen beyond a short distance because photons were constantly redirected by interactions with free electrons. Approximately 380,000 years after the beginning, temperatures fell to around 3,000 Kelvin. Electrons were finally able to combine with atomic nuclei to form stable neutral atoms. This event is known as recombination. Once electrons became bound into atoms, photons could travel much greater distances without scattering. The universe suddenly became transparent. Light that had previously been trapped began moving freely through space. That ancient radiation still exists today as the cosmic microwave background, stretched by expansion into microwave wavelengths and cooled to only a few degrees above absolute zero. The cosmic microwave background provides a remarkably detailed snapshot of the universe at that early time. Measurements reveal tiny temperature differences across the sky. These variations correspond to density fluctuations that were only a few parts in 100,000. Regions that were slightly denser contained a bit more mass and exerted slightly stronger gravitational attraction. Over billions of years, those minute irregularities grew into galaxies, clusters, and vast filaments of matter stretching across hundreds of millions of light-years. Every major structure visible today can ultimately be traced back to these subtle patterns imprinted in the early universe. After recombination, the universe entered a long interval known as the cosmic dark ages. Neutral hydrogen filled most of space. No stars yet existed. No galaxies shone across the darkness. Radiation from the cosmic microwave background continued traveling outward, gradually cooling as space expanded. The cosmos was not empty, but it lacked visible sources of light. Gravity quietly amplified the slight density differences inherited from earlier times. Across immense distances, matter slowly gathered into growing concentrations that would eventually become the first gravitationally bound structures. During the Dark Ages, dark matter played a dominant role in shaping cosmic evolution. Although invisible and still not directly identified, dark matter contributes far more mass than ordinary atomic matter. It does not interact strongly with light, allowing it to begin forming structures much earlier than normal matter. Vast dark matter halos emerged as gravity drew this unseen substance into denser regions. Ordinary gas later fell into these gravitational wells. In this way, dark matter provided the scaffolding upon which galaxies and stars would eventually develop. Over tens of millions of years, hydrogen and helium gas accumulated inside the densest dark matter halos. Gravity compressed these clouds. As gas fell inward, it heated through collisions. The balance between gravity pulling matter together and pressure resisting collapse gradually shifted. Certain regions became dense enough to continue contracting. These collapsing clouds marked the beginning of one of the most important transitions in cosmic history. The universe was approaching the birth of its first stars. The earliest stars likely formed around 100 to 200 million years after the Big Bang. These objects differed substantially from many stars seen today. Because the universe contained almost no heavy elements, cooling processes were less efficient. As a result, the first stars may have been extremely massive, perhaps dozens or even hundreds of times more massive than the Sun. Their cores reached extraordinary temperatures. Nuclear fusion began, converting hydrogen into helium and releasing enormous quantities of energy into previously dark regions of space. When the first stars ignited, the cosmic dark ages slowly came to an end. Ultraviolet radiation streamed outward through the surrounding hydrogen gas. For the first time, bright points of light appeared within the expanding universe. These stars transformed their environments. Radiation ionized nearby hydrogen atoms, separating electrons from nuclei once again. Expanding bubbles of ionized gas formed around stellar populations. Gradually, regions of darkness gave way to increasingly complex and luminous cosmic landscapes. The first generations of stars lived relatively short lives. Massive stars consumed their nuclear fuel rapidly. Many likely survived only a few million years before reaching the ends of their lifetimes. In their cores, fusion produced heavier elements including carbon, oxygen, silicon, and iron. When these stars died, some exploded as powerful supernovae. These events dispersed newly formed elements into surrounding space. The chemical enrichment of the universe had begun. Every heavier element necessary for rocky planets and biological chemistry originated through stellar processes such as these. As more stars formed, small protogalaxies emerged. Gravity merged these systems repeatedly. Streams of gas flowed into growing structures. Star formation accelerated in many regions. Over hundreds of millions of years, increasingly complex galaxies appeared throughout the universe. Their shapes evolved through collisions, mergers, and ongoing accretion of matter. The simple universe of hydrogen and helium gradually transformed into a cosmos containing diverse environments, from dense stellar nurseries to expanding intergalactic voids. A major transition known as cosmic reionization unfolded during the first billion years. Radiation from stars, galaxies, and perhaps early black holes spread through intergalactic space. Neutral hydrogen became increasingly ionized. The transparent universe we observe today emerged from this process. By roughly 1 billion years after the Big Bang, most intergalactic hydrogen had been reionized. Light could travel across vast cosmic distances with relatively little absorption, allowing galaxies to become visible over much of the observable universe. As billions of years passed, galaxies continued assembling into larger structures. Clusters and superclusters formed through gravitational attraction. Filaments of matter stretched across enormous distances, creating the cosmic web. Between these structures lay immense voids containing relatively little matter. On scales of hundreds of millions of light-years, the universe developed a recognizable large-scale architecture. Yet even these enormous patterns remained consistent with the tiny density fluctuations observed in the cosmic microwave background long before galaxies existed. Roughly 4.6 billion years ago, within a spiral arm of the galaxy now known as the Milky Way, a molecular cloud began collapsing under gravity. One region formed a young star that would become the Sun's surrounding gas and dust flattened into a rotating disk. Through countless collisions and gradual accumulation, planets formed from this material. The solar system emerged within an already mature galaxy populated by generations of stars that had enriched the surrounding medium with heavy elements produced through billions of years of stellar evolution. Today, the universe remains within what cosmologists call the stelliferous era. This is the age of stars. Nuclear fusion continues to power vast numbers of luminous objects throughout countless galaxies. Stars convert mass into energy according to well-understood physical principles. Hydrogen remains the primary fuel source for most stellar populations. The stelliferous era is characterized by active star formation, ongoing chemical enrichment, and the continuous recycling of matter through stellar birth and death. Although this era feels permanent on human timescales, it occupies only a limited chapter within the far longer future history of the cosmos. Star formation is not evenly distributed throughout the universe. Some galaxies convert gas into new stars rapidly, while others have become relatively quiet. Over cosmic time, the overall star formation rate has gradually declined. Billions of years ago, galaxies produced stars far more actively than they do today. Gas supplies are steadily consumed or expelled. The universe remains rich with stellar activity, but the peak period of star formation has already passed. The cosmos is slowly evolving toward a future with fewer opportunities for new stars to appear. Meanwhile, the expansion of the universe continues. Observations indicate that this expansion is accelerating due to a phenomenon known as dark energy. On sufficiently large scales, galaxies move farther apart as space itself expands. Over immense future timescales, distant galaxies beyond our local gravitational neighborhood will gradually become harder to observe. Their light will be stretched to longer wavelengths and weakened by expansion. The large-scale universe visible today will not remain accessible forever to future observers living trillions of years from now. Within our local region, gravity remains stronger than cosmic expansion. The Milky Way and the nearby Andromeda Galaxy are approaching one another at a speed of roughly 100 kilometers per second. Both galaxies contain vast dark matter halos whose mutual gravitational attraction dominates their motion. Although the distance between them remains enormous, the long-term outcome is well understood. Their trajectories indicate that a major galactic merger will occur several billion years in the future, fundamentally reshaping the structure of both systems. When the Milky Way and Andromeda eventually collide, individual stars are unlikely to strike one another directly because the average separation between stars is extremely large compared with their sizes. Instead, gravitational interactions will alter stellar orbits on a galactic scale. Spiral structures may be disrupted. Streams of stars will be flung into extended halos. Gas clouds may compress and trigger episodes of renewed star formation. Over time, repeated gravitational encounters will transform the two spiral galaxies into a single larger system often referred to by astronomers as Milkomeda. By the time this merger is complete, the universe will still remain deep within the stelliferous era. Stars will continue shining. White dwarfs, neutron stars, and black holes will accumulate as remnants of earlier generations. New stellar populations may emerge from remaining gas reservoirs. Yet the slow passage of cosmic time will continue directing the universe toward later epochs beyond the age of active star formation. Those distant eras lie far beyond the present moment. For now, our journey pauses at a universe still filled with galaxies, still illuminated by countless stars, and still evolving according to the same fundamental laws of gravity, thermodynamics, nuclear physics, and cosmic expansion that have governed its history since the beginning. For the universe itself, however, the passage of time does not pause, and as trillions upon trillions of years continue to accumulate, the familiar age of abundant starlight gradually gives way to a slower and quieter chapter in cosmic history known as the Degenerate Era. By approximately 100 trillion years after the beginning of the universe, most of the easily available hydrogen gas that once fueled star formation has either been incorporated into stars, locked within stellar remnants, or dispersed into regions where gravity can no longer efficiently gather it together. The brilliant stellar populations that characterized earlier epochs become increasingly rare. Galaxies that once contained hundreds of billions of active stars now consist largely of long-lived remnants orbiting through darkness. The universe remains structurally complex, but its visible activity has declined substantially. Thermodynamic gradients still exist, yet they are weaker and more localized than before. The rate at which new luminous objects emerge falls toward extremely low values, marking a fundamental transition in the overall behavior of cosmic matter. The final generations of stars are not massive blue giants or sun-like yellow stars. Instead, they are the smallest and most efficient hydrogen-burning stars that nature can produce. These red dwarfs possess masses only a fraction of that of the Sun. Their internal temperatures remain comparatively modest, and nuclear fusion proceeds at an exceptionally slow rate. Unlike larger stars, which exhaust their core fuel within millions or billions of years, low-mass red dwarfs can continue shining for trillions of years. Their extraordinary longevity arises from their efficient use of hydrogen. Convection circulates material throughout much of the star, allowing fresh fuel to continually reach the central fusion regions. As a result, they consume a far greater fraction of their available hydrogen before reaching the end of their lives. As cosmic time advances deeper into the future, red dwarfs increasingly dominate the remaining stellar population. Massive stars disappeared long ago. Intermediate stars became white dwarfs. The surviving red dwarfs represent the final stable engines of nuclear fusion on a cosmic scale. Their light is faint compared with the stars that illuminated earlier eras, but their persistence extends the stelliferous era far beyond what might otherwise be expected. Entire galaxies slowly dim as their brightest stars vanish, leaving these small and efficient objects as the primary remaining sources of visible radiation. The appearance of the universe during this period differs profoundly from the one known today. Accelerated expansion has carried distant galaxies far beyond observable horizons. The remnants of the local group remain gravitationally bound, but almost every galaxy beyond it has disappeared from view. Future observers, if any exist, would inhabit a cosmos appearing much smaller than the observable universe of the present day. Evidence for the primordial expansion of space would become increasingly difficult to detect. The visible sky would contain only the ancient remnants of nearby structures, surrounded by vast darkness stretching indefinitely beyond observation. Inside the oldest red dwarfs, nuclear fusion continues with remarkable patience. Every fusion reaction converts a tiny amount of mass into energy. The process remains governed by quantum tunneling, which allows protons to overcome electrostatic repulsion despite possessing insufficient classical energy. The probability of these tunneling events is extremely low, yet the enormous number of particles within stellar cores ensures a steady production of energy. Over trillions of years, these slow reactions maintain hydrostatic equilibrium, balancing gravity and preventing collapse. The stars evolve so gradually that their internal changes are almost imperceptible across timescales that would encompass the entire previous history of the universe many hundreds of times over. Eventually, even these exceptionally long-lived stars approach the limits of their fuel supplies. Hydrogen concentrations decline. Core compositions change. Luminosity slowly increases during the final stages of stellar evolution. Unlike larger stars, many red dwarfs never become red giants. Instead, they transition through much gentler evolutionary pathways. Their fusion processes cease without dramatic explosions. The universe experiences no spectacular conclusion to the age of stars. Rather, the final stellar lights fade through slow and orderly transformations governed by thermodynamics and the gradual exhaustion of nuclear energy sources. When fusion finally ends, gravity once again becomes the dominant influence within the former stellar core. Yet complete gravitational collapse does not occur. Quantum mechanics provides a new form of pressure. Electrons, which belong to a category of particles known as fermions, obey the Pauli exclusion principle. No two identical fermions can occupy precisely the same quantum state simultaneously. As matter becomes compressed, available quantum states fill. Additional compression forces electrons into increasingly energetic states. This generates electron degeneracy pressure, a fundamentally quantum mechanical resistance that does not depend primarily on temperature. It is this pressure that supports white dwarfs against further collapse. White dwarfs become among the most common objects of the degenerate era. These stellar remnants contain masses comparable to the Sun compressed into volumes similar to Earth. Densities become extraordinary. A teaspoon of white dwarf material would weigh many tons under terrestrial conditions. Atoms no longer resemble their familiar structure. Electrons form an extended degenerate quantum system surrounding densely packed atomic nuclei. The matter within these remnants exists in a state fundamentally different from ordinary solids, liquids, gases, or plasmas encountered during everyday experience. Although white dwarfs are born extremely hot, they possess no ongoing source of fusion energy. Their evolution becomes a slow process of cooling. Thermal energy gradually radiates into space. Because of their compact structure and immense heat capacity, cooling proceeds at a remarkably slow rate. Billions, trillions, and eventually quadrillions of years pass as temperatures steadily decline. Each white dwarf becomes a long-lived reservoir of stored thermal energy, releasing its remaining heat into an increasingly cold universe where alternative energy sources become progressively scarce. The internal composition of many white dwarfs consists primarily of carbon and oxygen nuclei produced during earlier phases of stellar evolution. At high temperatures, these nuclei behave within a dense ionic plasma. As cooling continues, thermal motion decreases. The nuclei become increasingly ordered. Eventually, conditions allow crystallization to occur. This process does not resemble the freezing of water into ice. Instead, positively charged nuclei arrange themselves into highly ordered lattice structures embedded within a sea of degenerate electrons. Quantum mechanical interactions and Coulomb forces determine the architecture of this exotic solid matter. Crystallization progresses gradually from the center outward. The densest regions cool first into ordered arrangements. Over immense timescales, larger fractions of the white dwarf become solid. The transformation releases latent heat, slightly slowing the cooling process. Observations of present-day white dwarfs already provide evidence that crystallization is occurring within some stellar remnants. In the deep future, however, the process becomes essentially complete. Entire objects composed largely of carbon and oxygen crystal lattices emerge as stable relics of long-extinct stars. These future crystalline remnants are sometimes informally described as cosmic diamonds, although the comparison is only partially accurate. Their structures differ greatly from familiar gemstones. The pressures, densities, and compositions involved are vastly beyond ordinary geological conditions. Nevertheless, the fundamental concept remains valid. Matter that once participated in active nuclear fusion eventually settles into rigid crystalline configurations. The energetic processes that once illuminated surrounding planetary systems have disappeared. What remains is a cold and highly ordered arrangement of nuclei and degenerate electrons slowly approaching thermal equilibrium with the wider universe. As white dwarfs continue cooling, their visible luminosities decline. Their surfaces emit progressively longer wavelengths of radiation. Bright white objects become redder, then infrared sources, and eventually nearly undetectable. The rate of cooling decreases as temperatures fall. Vast intervals pass between meaningful changes in appearance. A future observer could wait longer than the entire current age of the universe and witness only modest reductions in temperature. The remnants persist as fading embers within galaxies already transformed by incomprehensible spans of time. Eventually, theoretical models predict the emergence of objects sometimes called black dwarfs. These are white dwarfs that have cooled so extensively that they emit negligible visible radiation. The universe is currently far too young for any black dwarfs to exist. Even the oldest known white dwarfs remain relatively warm by comparison. Yet within the degenerate era, black dwarfs become common. They represent stellar remnants that have radiated away nearly all accessible thermal energy. Their temperatures approach those of the surrounding cosmic environment, and their visibility declines toward practical invisibility. Neutron stars also populate this future universe. These remnants arise from the collapse of more massive stars during earlier cosmic epochs. Their interiors contain matter compressed to extraordinary densities. Electrons and protons combine to form neutrons, producing objects only a few kilometers across yet containing masses greater than that of the Sun. Degeneracy pressure remains important here as well, although neutron degeneracy pressure and nuclear interactions become the dominant supporting mechanisms. Neutron stars cool steadily throughout the degenerate era, releasing residual thermal energy while gradually becoming darker and quieter. The surfaces of neutron stars possess remarkable physical properties. Gravity is so intense that a person standing there would experience forces vastly beyond human comprehension. Atomic structures become distorted. Thin layers of nuclei may organize into exotic configurations influenced by competition between nuclear attraction and electrostatic repulsion. Deeper within the star, matter may exist in states not fully understood by modern physics. Regardless of the exact details, these objects endure as long-lived reservoirs of degenerate matter, surviving long after ordinary stars have disappeared. Black holes also become increasingly important components of the cosmic inventory. Stellar mass black holes produced by ancient supernovae remain scattered throughout galaxies. Supermassive black holes occupy the centers of merged galactic remnants. Their gravitational influence continues shaping local dynamics even as the luminous populations around them fade. During the degenerate era, black holes often become among the most massive surviving structures within gravitationally bound systems. Yet even they do not dominate all aspects of cosmic evolution. Large populations of white dwarfs, neutron stars, and other compact remnants continue orbiting through the darkness alongside them. Over timescales approaching 10 to the 19th and 10 to the 20th years, gravitational interactions between stellar remnants gradually alter galactic structures. Close encounters transfer energy between orbiting objects. Some remnants are ejected into intergalactic space. Others migrate towards central regions. Galaxies slowly lose coherence. The process resembles a very gradual redistribution of orbital energy among countless bodies. No sudden catastrophe occurs. Instead, statistical mechanics governs the long-term evolution of these systems, producing increasingly diffuse distributions of matter over extraordinary intervals of time. The concept of relaxation becomes important in understanding this future evolution. Every gravitational encounter slightly modifies trajectories. Although individual changes are tiny, cumulative effects become significant across trillions upon trillions of years. Dense stellar systems slowly evaporate as lighter objects acquire sufficient energy to escape. Remaining populations become progressively smaller and more centrally concentrated. The process unfolds so gradually that no single moment marks a clear transition. Instead, galaxies evolve through a sequence of increasingly sparse configurations populated mainly by compact remnants. Planetary systems also experience long-term instability. Gravitational perturbations accumulate. Orbits shift. Some planets are ejected into interstellar space. Others collide with remnants of their parent stars. Countless worlds become rogue planets wandering through darkness without nearby sources of illumination. These objects retain internal energy for a time, but eventually they cool as well. The universe acquires vast populations of frozen bodies drifting between increasingly isolated concentrations of matter. As temperatures continue falling throughout cosmic history, quantum mechanical effects become increasingly prominent relative to thermal processes. Degenerate matter remains supported not by heat but by restrictions imposed on particle states. The distinction between classical and quantum behavior becomes especially important in describing the stability of white dwarfs and neutron stars. Even after thermal energy has largely dissipated, exclusion principles and quantum statistics continue determining the structure of matter. The persistence of these remnants therefore reflects not lingering warmth but fundamental properties of fermionic particles themselves. The future behavior of matter may depend critically on whether protons are truly stable. In the standard model of particle physics, proton decay does not occur. However, many theories that attempt to unify fundamental interactions predict that protons are ultimately unstable, though with extraordinarily long lifetimes. Experimental observations have not detected proton decay, establishing lower limits exceeding approximately 10 to the 34 years. If decay occurs, it is so rare that no measurable amount has yet been observed within present-day laboratories. Should proton decay prove real, the consequences for the degenerate era would be profound. Ordinary matter derives much of its persistence from the stability of protons within atomic nuclei. Over intervals approaching 10 to the 34, 10 to the 36, or perhaps 10 to the 40th years, individual protons could gradually transform into lighter particles. Various theoretical decay pathways have been proposed. The precise products depend on the underlying physical theory. Regardless of the details, the essential implication remains the same. Matter itself would slowly lose its integrity at the most fundamental level. Within black dwarfs, white dwarfs, planets, and other structures, proton decay would occur randomly throughout the material. Individual nuclei would occasionally disintegrate. The process would be extraordinarily sparse in time, yet the immense durations available ensure cumulative effects. Matter that appears perfectly stable across trillions of years would gradually erode when viewed across timescales many orders of magnitude longer. The structural framework of atoms would slowly dissolve as constituent particles transformed into radiation and lighter remnants. A remarkable feature of proton decay is its statistical character. No nucleus possesses knowledge of when a decay event will occur. Quantum mechanics provides probabilities rather than precise schedules. A proton may survive for durations vastly exceeding the average lifetime, while another decays earlier. Across enormous populations of particles, predictable averages emerge. Across individual particles, outcomes remain fundamentally probabilistic. This quantum uncertainty becomes one of the central mechanisms governing the fate of matter in the distant future. As proton decay progresses, planetary bodies gradually lose mass. Crystalline stellar remnants slowly diminish. Atomic lattices that persisted for incomprehensible intervals begin to break apart. The process remains extremely gentle. No dramatic explosions accompany most decay events. Instead, energy is released incrementally through countless microscopic transformations distributed throughout matter. Thermodynamics continues directing energy toward increasingly diffuse forms. Ordered structures become harder to maintain as their constituent particles disappear one by one. The interiors of black dwarfs undergo particularly interesting evolution if proton decay occurs. These objects begin as highly ordered configurations of carbon, oxygen, and heavier nuclei embedded within degenerate electron systems. Over immense timescales, decay processes alter nuclear compositions. Degeneracy pressure weakens as particle populations change. The remnant gradually loses mass and structural complexity. Matter that once formed the core of a living star slowly transitions into increasingly sparse distributions of elementary particles and radiation. Even in the absence of proton decay, other long-term processes may influence degenerate matter. Quantum tunneling can occasionally permit nuclear reactions within extremely cold environments. Some theoretical studies suggest that black dwarfs could eventually experience rare fusion events after unimaginable periods. These possibilities remain highly speculative and occur on timescales so vast that conventional intuition offers little guidance. Nevertheless, they illustrate that quantum mechanics continues operating regardless of temperature, allowing exceedingly improbable events to accumulate significance when enough time is available. Throughout the degenerate era, entropy continues increasing. Energy gradients become weaker. Accessible free energy declines. The universe does not cease evolving, but the pace of observable change slows dramatically. Processes that once unfolded in seconds, years, or millions of years are replaced by events requiring intervals many trillions of times longer. The characteristic rhythm of cosmic evolution changes fundamentally. Motion remains. Interactions continue. Yet meaningful transformations become increasingly separated by vast expanses of quiet time. By the time the universe approaches the farthest reaches of the degenerate era, active stars have disappeared. Most visible light sources are gone. Galactic structures have thinned. White dwarfs have become black dwarfs. Neutron stars have cooled. Matter itself may be slowly dissolving through proton decay. The cosmos remains governed by the same physical laws that shaped the first moments after the Big Bang. But those laws now operate within an environment profoundly different from the luminous universe that existed billions of years earlier. What remains is a population of ancient remnants, gradually surrendering their stored order to the long and patient progression of thermodynamic equilibrium, while the deep future continues extending far beyond even these extraordinary spans of time. Beyond those fading remnants, cosmic evolution enters a period in which nearly all familiar forms of matter have either transformed, dispersed, or ceased to play a dominant role in the large-scale behavior of the universe. The era that follows is commonly known as the Black Hole Era, a chapter extending across intervals so immense that even the degenerate era appears brief by comparison. By this stage, most stars vanished long ago. The last stable sources of fusion energy are gone. Planetary systems no longer exist in recognizable forms. If proton decay occurs, much ordinary matter has already dissolved into lighter particles and radiation. What remains are the most durable gravitational structures produced during the earlier history of the cosmos, black holes of many different masses, isolated within a universe of extraordinary emptiness. The appearance of space during this epoch differs profoundly from any previous age. Galaxies no longer shine. Vast stellar populations are absent. The darkness is not merely the absence of visible light, but the consequence of a universe whose accessible energy reservoirs have largely been exhausted. Distances between surviving objects become immense. Expansion continues. Radiation becomes increasingly dilute. The cosmos contains structure, but that structure is sparse, cold, and separated by intervals of emptiness so large that conventional descriptions of distance lose much of their intuitive meaning. Black holes themselves are products of earlier eras. Some originated from the collapse of massive stars. Others grew through mergers with neighboring black holes. The largest formed in galactic centers, accumulating matter across billions of years before the luminous age came to an end. During the black hole era, these objects become the dominant repositories of remaining mass and energy. Their gravitational fields persist even as nearly everything else gradually disappears from cosmic significance. According to classical general relativity, a black hole is defined by the presence of an event horizon. This boundary separates regions from which escape remains possible from regions where all future trajectories lead inward. Nothing moving slower than light can emerge once it crosses this threshold. Classical descriptions therefore suggest that black holes should persist indefinitely. They absorb matter, retain mass, and remain stable forever. Yet quantum mechanics introduces an additional layer of behavior that fundamentally alters this conclusion. The key insight emerged during the 20th century through the work of physicists exploring the relationship between gravitation, quantum fields, and thermodynamics. The resulting picture revealed that black holes are not completely black. Instead, quantum effects occurring near the event horizon allow black holes to emit radiation. This phenomenon is now known as Hawking radiation. Although extraordinarily weak for large black holes, it implies that every isolated black hole slowly loses energy and mass over time. To understand this process, it is useful to consider the quantum nature of empty space. In quantum field theory, a perfect vacuum is not truly empty. Even when no real particles are present, quantum fields continue exhibiting fluctuations. These fluctuations arise because uncertainty principles prevent fields from remaining perfectly motionless. Temporary excitations occur continuously throughout space. Such behavior does not violate conservation laws because the fluctuations exist within limits allowed by quantum mechanics. Near an event horizon, these vacuum fluctuations interact with the extreme geometry of space-time. The popular description often refers to virtual particle pairs appearing near the horizon, with one particle escaping while the other falls inward. Although this picture is simplified, it captures part of the underlying idea. The curved spacetime surrounding a black hole alters the behavior of quantum fields in such a way that distant observers detect a faint stream of particles emerging from the vicinity of the horizon. The emitted radiation possesses a thermal spectrum. In other words, the black hole behaves as though it has a temperature. This was a remarkable discovery because temperature is normally associated with systems containing microscopic degrees of freedom. Black holes, which seemed to erase information about the material that formed them, unexpectedly exhibited thermodynamic properties. The temperature depends inversely upon mass. Large black holes are colder. Small black holes are warmer. This relationship plays a central role in determining their future evolution. For a stellar mass black hole containing several times the mass of the Sun, the Hawking temperature is extraordinarily low. It is far below the temperature of the present cosmic microwave background. Even after the microwave background has cooled through cosmic expansion, such a black hole emits only tiny amounts of radiation. The associated power output is minuscule. If placed near ordinary astrophysical objects, the emitted energy would be essentially impossible to notice. Yet over sufficiently long timescales, even an extremely small energy loss becomes significant. The thermodynamic behavior of black holes can be described through entropy as well. The entropy associated with a black hole is proportional not to its volume but to the area of its event horizon. This relationship was among the first hints that space-time geometry, information, and quantum mechanics might be deeply connected. A larger horizon corresponds to greater entropy. Consequently, supermassive black holes contain astonishing amounts of entropy, exceeding that of most other known physical systems. As the black hole era progresses, the surrounding universe becomes increasingly cold. Radiation left over from earlier epochs continues stretching to longer wavelengths. Matter becomes scarce. Interactions between surviving objects occur less frequently. Eventually, many black holes become effectively isolated. Under these conditions, Hawking radiation no longer competes with incoming energy. The black holes begin a slow and steady process of net evaporation. The rate of evaporation depends strongly upon mass. A more massive black hole possesses a larger event horizon and a lower temperature. Because temperature remains low, particle emission occurs slowly. Consequently, large black holes survive far longer than smaller ones. This inverse relationship produces one of the most dramatic timescale differences in all of physics. Doubling the mass of a black hole more than doubles its lifetime. Increasing mass by enormous factors extends survival times to almost unimaginable durations. The smallest surviving black holes evaporate first. Stellar remnants formed during ancient supernova explosions slowly radiate away their energy. The process remains nearly imperceptible for most of their existence. For vast intervals, their masses change only slightly. An observer monitoring such a black hole over millions, billions, or even trillions of years would notice essentially no difference. Yet the cumulative effect continues without interruption. Every emitted particle carries away energy. Every loss of energy corresponds to a tiny reduction in mass. As mass decreases, temperature increases. This creates a feedback mechanism unique to evaporating black holes. A smaller black hole radiates more efficiently than a larger one. Increased radiation accelerates mass loss. Accelerated mass loss further increases temperature. The cycle continues. For most of a black hole's lifetime, the effect remains weak, but during the final stages it becomes increasingly important. Evaporation proceeds ever more rapidly as the remaining mass shrinks. The particles emitted through Hawking radiation depend on the temperature of the black hole. Extremely cold black holes emit primarily low-energy photons and other light particles. As temperatures rise, additional particle species become energetically accessible. Electrons, positrons, neutrinos, and eventually heavier particles may be produced. The precise spectrum evolves throughout the lifetime of the black hole, reflecting the changing thermodynamic conditions associated with its decreasing mass. Quantum field theory predicts that particle creation near an event horizon does not occur in discrete bursts separated by long intervals. Instead, it is better understood as a continuous thermal process described statistically. Individual particles appear unpredictably, yet the overall emission rate follows precise mathematical relationships. These relationships connect gravity, quantum mechanics, and thermodynamics in ways that remain among the deepest topics in modern theoretical physics. During the majority of the black hole era, the universe contains little activity beyond these faint emissions. Vast regions of space remain almost entirely empty. Occasionally a photon emerges from a distant black hole. Elsewhere, a neutrino drifts through darkness. Such events are separated by enormous distances and times. The universe does not become static, but its evolution slows to a pace difficult to compare with anything from earlier cosmic history. Supermassive black holes dominate the long-term future because of their immense masses. Objects containing millions or billions of solar masses possess correspondingly enormous lifetimes. Their Hawking temperatures are extraordinarily small, often far below temperatures associated with almost any other physical system. They lose mass so slowly that the entire preceding history of the universe becomes negligible compared with the duration required for significant evaporation. Many supermassive black holes originated within galactic centers during the stelliferous era. Through mergers and accretion, they accumulated extraordinary amounts of matter. When galaxies merged, their central black holes often migrated toward common centers and eventually combined. The resulting objects grew progressively larger. By the onset of the black hole era, some may contain masses exceeding billions of suns. These become the longest-lived gravitational structures known within standard cosmological models. The lifetime of a black hole scales approximately with the cube of its mass. This dependence creates enormous disparities. A black hole with 10 times the mass of another survives roughly 1,000 times longer. When masses differ by factors of millions or billions, the corresponding lifetimes become staggeringly different. Stellar remnants evaporate long before the largest supermassive black holes begin experiencing substantial reductions in mass. Throughout these epochs, space-time itself continues expanding. Distances between isolated regions increase. Horizons associated with cosmic expansion limit communication across vast scales. Radiation emitted by one black hole may never encounter another. Energy becomes distributed across increasingly enormous volumes. Thermodynamic equilibrium remains a moving target because the geometry of the universe continues evolving even while local processes proceed toward greater entropy. As trillions of years pass, the number of surviving black holes gradually decreases. Smaller remnants vanish first. Intermediate mass objects follow. The cosmic inventory becomes increasingly dominated by the largest survivors. The universe grows simpler in one sense, containing fewer types of active structures, yet the timescales governing remaining processes become ever more extreme. Change persists, but meaningful transitions require intervals that dwarf everything that came before. One remarkable aspect of Hawking radiation is that it carries away energy while preserving the overall consistency of thermodynamic laws. The emitted particles contribute to the entropy of the surrounding universe. Black hole entropy decreases as the horizon shrinks, but the entropy associated with outgoing radiation increases. The total entropy continues moving toward larger values, maintaining the general thermodynamic direction that has characterized cosmic evolution since the earliest moments after the Big Bang. The relationship between information and evaporation remains an area of active theoretical investigation. Classical descriptions suggest that information entering a black hole becomes inaccessible. Quantum mechanics, however, generally preserves information through time evolution. Reconciling these principles produced one of the most important problems in modern theoretical physics. Various proposed resolutions involve subtle mechanisms by which information may be encoded within outgoing radiation or within deeper structures associated with spacetime itself. Regardless of the ultimate resolution of these theoretical questions, the large-scale thermodynamic prediction remains unchanged. Isolated black holes emit radiation and lose mass. Given enough time, complete evaporation becomes inevitable. The process is not driven by external forces. It emerges naturally from the interaction between quantum fields and curved spacetime. In this sense, Black hole evaporation represents one of the most profound examples of quantum mechanics influencing the fate of astronomical objects. For a stellar mass black hole, the evaporation time is roughly 10 to the 6 to 7th years. Such a number exceeds the current age of the universe by an almost inconceivable factor. Yet within the chronology of the black hole era, even this duration represents only an early chapter. Larger black holes continue existing long after stellar remnants have disappeared, maintaining their slow release of radiation into an increasingly empty cosmos. When a black hole has lost most of its mass, the final stages of evaporation become dramatically different from the long quiet beginning. Temperatures rise substantially. Particle emission intensifies. The black hole radiates energy at increasingly rapid rates. The final interval occupies only a tiny fraction of the total lifetime, yet it contains much of the visible activity associated with the evaporation process. What was once nearly undetectable becomes comparatively energetic, though still occurring within an otherwise dark and empty universe. The exact behavior of the final moments remains uncertain because evaporation eventually approaches regimes where both quantum mechanics and gravity become simultaneously important. Existing theories describe much of the process successfully, but a complete theory of quantum gravity remains unfinished. Consequently, predictions concerning the ultimate endpoint contain some uncertainty. Nevertheless, most models agree that the black hole does not persist indefinitely. Its mass is eventually converted into radiation and elementary particles. For supermassive black holes, the relevant timescales extend toward 10 to the 90th, 10 to the 95th, and even around 10 to the 100 years depending upon mass. These numbers are so large that ordinary language struggles to convey their magnitude. Entire eras of cosmic evolution unfold within intervals that remain negligible compared with the lifetimes of the largest black holes. Their persistence dominates the chronology of the distant future. During these immense spans, the universe becomes increasingly dilute. Radiation from evaporated black holes spreads outward. Wavelengths stretch. Particle densities fall. Interactions become rare. The cosmos approaches conditions in which surviving forms of organized structure are extraordinarily uncommon. Yet the slow evaporation of the largest black holes continues, ensuring that complete thermodynamic relaxation remains unfinished. Eventually, only the most massive black holes remain. Their event horizons still contain enormous entropy. Their temperatures remain extremely low. They emit particles at astonishingly slow rates. Nevertheless, the underlying process never stops. Quantum fields continue fluctuating. Radiation continues escaping. Mass continues decreasing. The direction of evolution remains unchanged regardless of how slowly it proceeds. If one could observe such a universe over intervals approaching the full lifetime of a giant black hole, the dominant visible phenomenon would be gradual evaporation itself. No stars would rise. No galaxies would collide. No planetary systems would orbit luminous suns. The principal source of new particles would be the black holes. Their slow conversion of gravitational mass into radiation would define the remaining activity of the cosmos. As each supermassive black hole nears its end, temperature rises sharply. Emission intensifies. A long era of new perfect stillness concludes with a comparatively brief period of accelerated particle production. The black hole rapidly sheds its remaining mass. Radiation streams outward into surrounding emptiness. The horizon contracts toward ever smaller dimensions. Finally, the object ceases to exist as a black hole at all, leaving only the products of its evaporation behind. The disappearance of one black hole does not immediately transform the wider universe. Distances remain enormous. Other surviving black holes continue evolving according to their own schedules. Yet with each evaporation event, the total population declines. The era advances toward its conclusion. Fewer horizons remain. Less mass remains locked within gravitational reservoirs. More energy exists in diffuse and weakly interacting forms distributed across expanding space. Near the end of the black hole era, only the largest and longest-lived objects persist. Their evaporation represents the final chapter of black hole dominance. When they eventually disappear, the universe enters conditions unlike any previous epoch. The structures that once concentrated matter and entropy into compact regions are gone. Only thin distributions of radiation, elementary particles, and whatever stable remnants nature ultimately permits continue occupying the vastness of space. The black hole era therefore serves as an extraordinarily long transition between a universe that still contains massive gravitational structures and a future in which even those structures no longer survive. Across intervals extending toward 10 to the 100 years, quantum mechanics gradually dismantles the most durable objects ever produced by cosmic evolution. The process is slow, orderly, and governed by precise physical laws. Long after stars have vanished and matter has faded, the quiet emission of Hawking radiation continues shaping the destiny of the universe one particle at a time, carrying the cosmos toward an even deeper and more rarefied future that lies beyond the final evaporation of the last black hole. After the last black hole completes its evaporation, the universe enters the final known chapter of its long thermodynamic evolution, a period commonly described as the Dark Era, in which no large gravitational structures remain and nearly all processes familiar from earlier cosmic history have come to an end. The disappearance of the final event horizon marks a significant transition in the inventory of the cosmos. For the first time since the formation of the earliest structures, there are no stars, no stellar remnants, no galaxies, and no black holes. Matter, if any remains at all, exists only in extremely diffuse forms. The universe has not ceased to exist, nor have the laws of physics changed. Rather, the physical contents of space have become extraordinarily simple. Most of the complexity accumulated across earlier eras has been erased by the relentless increase of entropy and the gradual redistribution of energy into increasingly uniform configurations. At this stage, the average separation between surviving particles is immense. Distances that were once associated with clusters of galaxies become insignificant compared with the scales now characterizing the universe. Expansion has continued for intervals exceeding 10 to the 100 years. Regions that were once neighbors have long since disappeared beyond one another's cosmological horizons. Space remains populated by quantum fields, but localized concentrations of energy are exceptionally rare. The universe is not completely empty, yet it approaches a condition that earlier observers might reasonably describe as an almost perfect vacuum. The temperature of the universe continues falling as expansion stretches every remaining wavelength of radiation. Photons emitted during the final evaporation of black holes travel through expanding space, losing energy through cosmological redshift. Their wavelengths become progressively longer. Frequencies decline. Energies decrease. The radiation does not disappear, but its ability to participate in meaningful physical interactions becomes increasingly limited. The universe contains photons, yet those photons carry extraordinarily small amounts of usable energy. One of the defining features of the Dark Era is the absence of significant thermodynamic gradients. Earlier epochs contained stars hotter than surrounding space, planets warmer than their environments, and black holes with measurable temperatures. Such differences allowed energy to flow from one region to another. Those flows powered physical change. By contrast, the Dark Era approaches a state in which temperature differences become vanishingly small. The universe remains dynamic at microscopic levels, but large-scale sources of free energy have effectively disappeared. The concept of heat death is closely associated with this period. Heat death does not imply destruction, collapse, or sudden termination. Instead, it refers to a condition in which entropy approaches a maximum value and useful energy becomes unavailable for performing work. Physical laws continue operating exactly as before. Particles move. Radiation propagates. Quantum processes occur. Yet there are no substantial energy gradients capable of sustaining organized activity on large scales. The universe settles into a condition of extreme thermodynamic uniformity. If proton decay occurred during the degenerate era, ordinary baryonic matter has already largely vanished by this point. Atomic nuclei that once formed stars, planets, and biological systems have transformed into lighter particles and radiation. The familiar matter that dominated human experience has become only a small and fading memory in the chronology of the cosmos. Surviving particles are increasingly likely to belong to categories that interact weakly and carry little energy relative to earlier epochs. Among the particles expected to persist are electrons and positrons, provided no additional decay mechanisms remove them. These leptons may remain stable indefinitely according to current observations. If so, they continue existing throughout the Dark Era as isolated particles distributed across immense expanses of space. Their interactions become extraordinarily rare because average densities continue falling. A particle may travel for durations exceeding earlier cosmic ages without encountering another particle capable of producing a significant interaction. Neutrinos also remain important inhabitants of the distant future. These particles interact only through gravity and the weak nuclear force. Their masses are extremely small, and their interaction probabilities are correspondingly tiny. The universe already contains enormous numbers of neutrinos today, and many survive throughout the Dark Era. As expansion proceeds, their energies continue decreasing. They become increasingly cold, diffuse, and difficult to distinguish from the background conditions of the universe itself. Photons represent another major component of the future cosmos. Every photon travels at the speed of light, yet cosmological expansion continuously stretches its wavelength. A photon that once possessed substantial energy gradually loses that energy as the universe grows larger. Eventually, its wavelength may exceed scales that earlier civilizations would have considered astronomically large. The photon continues existing, but its contribution to local physical processes becomes negligible because its energy approaches extraordinarily small values. The Dark Era therefore contains a sparse population of low-energy particles drifting through an expanding vacuum. Unlike earlier epochs, these particles rarely gather into larger structures. Gravity becomes ineffective at assembling new systems because the densities involved are far too low. The ingredients that once produced galaxies, stars, and planets remain dispersed across volumes so vast that meaningful concentrations no longer emerge. Structure formation, which dominated the first billions of years of cosmic history, has effectively ended. Quantum mechanics nevertheless remains active. Even in an almost empty universe, quantum fields continue existing throughout space. Fluctuations remain possible. Uncertainty relations continue governing measurable quantities. The absence of stars and galaxies does not imply the absence of physics. Rather, The remaining physical processes occur at scales and rates far removed from those associated with earlier cosmic evolution. The universe becomes quieter, but not fundamentally inactive. Some theoretical models suggest that exceedingly rare quantum events may occur over immense timescales. Given enough time, even extraordinarily improbable processes can acquire non-zero probabilities. The challenge lies in the fact that these probabilities may correspond to durations so vast that conventional numerical descriptions become difficult to interpret. Such possibilities remain subjects of theoretical investigation rather than established predictions, yet they illustrate how quantum mechanics continues operating regardless of how empty the universe becomes. One important aspect of the dark era concerns the continued role of dark energy. Observations indicate that dark energy currently drives the accelerated expansion of the universe. If dark energy remains constant into the far future, its influence never disappears. Instead, it becomes increasingly dominant because matter and radiation densities continue decreasing while the energy density associated with dark energy remains approximately unchanged. Consequently, the large-scale geometry of the universe becomes progressively more influenced by this component. As expansion accelerates, regions of space become isolated from one another. Horizons emerge that limit the portion of the universe accessible to any observer. Events occurring beyond these horizons can never transmit information across the expanding separation. During the Dark Era, this isolation becomes even more pronounced than in earlier epochs. Surviving particles occupy increasingly disconnected regions of spacetime, each separated from others by distances that grow faster than light can bridge through ordinary propagation. The geometry associated with an accelerating universe possesses thermodynamic implications of its own. Horizons linked to expansion can be assigned temperatures and entropies in ways analogous to certain aspects of black hole physics. Although these temperatures are extraordinarily small, they remind us that thermodynamics remains deeply connected to the structure of spacetime itself. Even when conventional matter has disappeared, the relationship between information, geometry, and entropy continues playing a role in theoretical descriptions of the cosmos. The average density of matter during the Dark Era becomes almost inconceivably low. Volumes once containing galaxies now contain only scattered particles. Distances between neighboring particles increase continuously. Encounters become rare enough that meaningful interaction rates approach zero. Physical systems that depend upon frequent collisions cannot exist under such conditions. The universe resembles an immense arena whose contents have been diluted across an ever-expanding stage. Despite this dilution, conservation laws continue governing the evolution of surviving particles. Energy, momentum, electric charge, and other conserved quantities remain constrained by the same principles that operated during the earliest moments after the Big Bang. The universe may appear empty, but the mathematical structure underlying physical law remains intact. The Dark Era is therefore not a breakdown of physics. It is the long-term consequence of physics operating consistently across unimaginable durations of time. Thermodynamic equilibrium in this context should not be imagined as complete stillness. Individual particles continue moving. Photons continue traveling. Quantum fields continue fluctuating. What changes is the availability of organized energy differences. Earlier eras contained regions capable of driving sustained transformation. The Dark Era contains very few such opportunities. Evolution persists primarily through subtle statistical processes rather than through dramatic astrophysical events. If electrons remain absolutely stable, they may become among the longest-lived particles in the universe. Their persistence would allow the dark era to extend indefinitely into the future. A sparse gas of isolated leptons and low-energy radiation could continue occupying expanding space for durations beyond any finite numerical scale commonly used in cosmology. Time itself continues. Physical law continues. Yet little remains to distinguish one epoch from another except the ongoing increase of spatial separation and the gradual reduction of energy densities. Another consequence of continual expansion is the ongoing decrease in the frequency of interactions among surviving particles. Even when two particles possess the ability to interact, the probability that they encounter one another becomes increasingly small. Expansion effectively removes opportunities for interaction by enlarging the volume available to the particles. The result is a universe in which isolation becomes the dominant physical condition rather than the exception. The concept of a vacuum acquires particular importance during this era. In everyday language, a vacuum is often described as empty space. In quantum field theory, however, the vacuum is a physical state possessing structure. Fields exist even when particles are absent. Vacuum energy, fluctuations, and other quantum properties remain part of the universe regardless of how sparse its particle content becomes. Consequently, the dark era is not a transition into nothingness. It is a transition into a cosmos dominated by the properties of nearly empty spacetime itself. From the perspective of thermodynamics, the journey toward maximum entropy represents the gradual elimination of preferred arrangements. Stars, planets, galaxies, and black holes were highly structured configurations. Their existence reflected the presence of energy gradients established during earlier cosmic evolution. As those structures disappeared, energy became distributed more uniformly. The dark era continues this trend. The remaining particles and radiation occupy states increasingly close to statistical equilibrium across the accessible universe. Even the passage of time becomes difficult to characterize in familiar ways. Human experience evolved within environments rich in periodic processes. Planetary rotations defined days. Orbital motions defined years. Stellar evolution provided long-term clocks. During the Dark Era, such reference systems no longer exist. Time remains a fundamental parameter in physical equations, yet the universe contains few events suitable for measuring its passage. Durations become meaningful primarily through theoretical descriptions rather than through observable cycles. If dark energy remains constant forever, expansion never stops. Space continues growing larger. Radiation continues redshifting. Particle densities continue declining. The overall trajectory of cosmic evolution remains unchanged. Every surviving component becomes increasingly isolated. The universe approaches conditions that differ only gradually from one era to the next, creating an extended future characterized by extraordinary stability and minimal large-scale change. Yet despite this apparent simplicity, the Dark Era represents the culmination of everything that came before. Every photon present owes its existence to earlier physical processes. Every surviving particle traces its history through the formation of stars, galaxies, and the primordial universe itself. The final state of the cosmos emerges not from a separate set of laws but from the cumulative consequences of the same laws operating consistently across intervals extending from fractions of a second after the Big Bang to durations exceeding 10 to the 100 years and beyond. Within that vast future, the universe continues existing as a sparse collection of low-energy particles, stretched wavelengths, quantum fields, and expanding space-time. Complexity has faded. Structure has dissolved. Thermodynamic gradients have nearly vanished. Yet the fundamental framework of physics remains present everywhere. The Dark Era therefore stands not as an ending in the ordinary sense, but as the most extended and tranquil chapter in the known chronology of cosmic time, a chapter whose full duration reaches far beyond the disappearance of the last black hole and extends into a future where emptiness itself becomes the defining feature of existence. Beyond even that immense future, theoretical physics continues to explore whether any remaining processes might still occur within a universe approaching its maximum possible entropy. One possibility concerns the long-term behavior of matter in scenarios where proton decay does not occur. If protons are perfectly stable, then a small fraction of ordinary matter could survive far beyond the epochs discussed previously. White dwarf remnants that escaped destruction during earlier eras might continue existing as extremely cold crystalline objects. Across durations so vast that even the black hole era becomes a distant memory, quantum tunneling could slowly alter their internal nuclear composition. These processes are extraordinarily improbable on ordinary timescales, yet probability accumulates when time extends toward values such as 10 to the 1500 years and beyond. Within such ancient remnants, nuclei occupy densely packed arrangements. Classical physics would predict little change once temperatures become negligible. Quantum mechanics, however, allows particles to penetrate energy barriers through tunneling. Although the probability of any individual tunneling event remains tiny, immense spans of time permit rare reactions to occur. Gradually, lighter nuclei may combine into heavier configurations without the need for the high temperatures normally associated with stellar fusion. The process unfolds with extraordinary slowness and affects only isolated regions over incomprehensible durations. Some theoretical studies suggest that these reactions could eventually favor the formation of increasingly stable nuclei. Iron occupies a special position in nuclear physics because it lies near the peak of binding energy per nucleon. Fusion of lighter elements generally releases energy when moving toward iron, while fission of heavier elements can do the same. As a result, matter subjected to extremely long periods of rare quantum transformations may slowly evolve toward iron-rich compositions. The hypothetical remnants produced through this mechanism are sometimes referred to as iron stars. An iron star, if such an object ever forms, would differ dramatically from ordinary stars. It would not generate light through fusion. It would not possess an active core. It would simply represent matter that has reached an exceptionally stable nuclear configuration after unimaginable spans of quantum evolution. The object would remain cold, dark, and nearly invisible. Its significance lies not in brightness but in its status as one of the most stable forms of baryonic matter allowed by known nuclear physics. The timescales associated with this possibility are so extreme that they exceed almost every other process discussed in cosmology. Entire eras of stars, galaxies, black holes, and particle decay would occupy comparatively brief intervals. Whether iron stars actually form depends strongly upon the stability of protons and the precise details of nuclear tunneling probabilities. Current observations cannot test such predictions directly because the required durations exceed the age of the universe by extraordinary factors. If proton decay does occur, however, iron stars never become permanent structures. Their constituent particles eventually disintegrate. The long-term trend toward increasing entropy continues uninterrupted. Matter that once occupied organized nuclear arrangements gradually transforms into lighter particles and radiation. The distinction between different forms of matter becomes less important as the universe moves toward increasingly diffuse states. Stability remains relative rather than absolute. Another question concerns the ultimate nature of the vacuum itself. Modern quantum field theory describes empty space as a state possessing measurable properties. The vacuum is not a simple absence of substance. Instead, it represents the lowest energy configuration available to quantum fields. Yet physicists do not know with certainty whether the vacuum currently observed throughout the universe is truly the lowest possible state or merely a metastable configuration that appears stable over extremely long periods. If the vacuum is absolutely stable, then no deeper energy state exists. In that case, the large-scale structure of physical law remains unchanged indefinitely. Particle masses, interaction strengths, and fundamental constants persist exactly as they are. The dark era continues without any dramatic alteration of the underlying framework of reality. Expansion proceeds. Particles drift. Radiation redshifts. The universe remains governed by familiar physical principles across arbitrarily long durations. If the vacuum is metastable, a different possibility emerges. Quantum tunneling could allow a transition to a lower energy vacuum state. Such an event would begin within a microscopic region and expand outward at approximately the speed of light. The new vacuum would possess different physical properties. Particle masses and interactions could change. Structures adapted to the previous vacuum would no longer remain stable. This process is known as vacuum decay. Although theoretically possible, current evidence provides no indication that such a transition is imminent. Indeed, if it can occur at all, the expected timescales may vastly exceed even those associated with black hole evaporation. For the purposes of most long-term cosmological models, the vacuum is treated as effectively stable. Under that assumption, the future becomes dominated not by dramatic transformations but by continuing dilution. Every surviving particle becomes increasingly isolated. Radiation wavelengths continue stretching. Energy densities continue falling. The universe approaches conditions in which meaningful change occurs only through extraordinarily rare quantum events distributed across immense expanses of space-time. At sufficiently late times, the distinction between individual epochs begins to lose practical meaning. There are no galaxies whose evolution can be tracked. There are no stars marking stages of development. There are no black holes undergoing measurable evaporation. Instead, the universe consists primarily of low-energy fields and particles occupying an expanding background shaped by dark energy. Time continues, but observable milestones become increasingly scarce. The concept of thermal equilibrium reaches its fullest expression during this period. Earlier stages of cosmic history contained gradients of temperature, density, and gravitational potential. Those gradients drove the formation of structure. They powered stars. They generated chemical complexity. By the deepest phases of the dark era, such gradients have nearly vanished. Remaining energy becomes distributed with remarkable uniformity across accessible regions of space-time. Entropy approaches its maximum attainable value under the prevailing physical conditions. In thermodynamic language, the universe has exhausted nearly all opportunities for performing useful work. Work requires differences. It requires energy concentrated in one location and absent in another. It requires gradients that permit flow. As equilibrium is approached, those differences diminish. The universe remains physically real, yet it no longer contains significant reservoirs capable of driving large-scale transformation. This condition is the essence of cosmic heat death. Heat death does not imply motionlessness. Photons continue moving at the speed of light. Neutrinos continue traversing space. Electrons, if stable, continue existing. Quantum fluctuations remain present. The defining characteristic is not the absence of activity, but the absence of organized energy flow. Processes occur, but they do not collectively build complexity. Instead, they maintain a state already close to thermodynamic equilibrium. Dark energy continues playing a dominant role in shaping large-scale geometry. If its density remains constant, expansion accelerates indefinitely. Every region becomes increasingly isolated from every other region. Horizons persist. Accessible volumes remain finite even while the total universe may be vastly larger. The observable portion available to any hypothetical observer becomes increasingly empty. The future is characterized not by accumulation but by separation. By this stage, the chronology that began with the hot, dense early universe has completed its thermodynamic arc. The first moments after the Big Bang were defined by extraordinary temperatures and densities. The middle epochs contained stars, galaxies, planets, and black holes. The final epochs contain dilute radiation, sparse particles, and expanding space-time. The same physical laws operate throughout, yet the conditions under which they act have changed profoundly over cosmic history. The 100th and final fact in this journey is therefore a simple consequence of thermodynamics itself. If current physical understanding remains valid across the deepest future, the universe approaches a state in which no further large-scale evolution is possible because nearly every accessible source of free energy has been exhausted, leaving a cosmos that persists indefinitely in near perfect equilibrium beneath the continuing expansion of space. Our journey has now crossed a range of time extending from fractions of a second after the beginning of the observable universe to intervals so vast that ordinary numbers become difficult to imagine. Along the way, every familiar structure emerged, evolved, and eventually faded according to the same physical laws. The earliest plasma cooled. The first atoms formed. Gravity assembled galaxies. Stars illuminated the cosmos. Heavy elements appeared. Planets emerged. Stellar remnants accumulated. Black holes dominated. And finally, even those most durable structures disappeared into the long future of the Dark Era. Throughout this chronology, no stage existed outside physics. Every transformation arose from interactions governed by gravity, thermodynamics, quantum mechanics, and the expansion of space. The universe did not move toward a predetermined destination. Instead, each era followed naturally from the conditions established by the one before it. Small fluctuations in the early universe became galaxies. Nuclear fusion became starlight. Starlight became heavier elements. Heavier elements became planets and future generations of stars. Over immense durations, those same processes gradually consumed their available energy and brought the universe toward equilibrium. One of the most remarkable features of this history is its scale. Human lifetimes occupy only a tiny interval within cosmic time. Civilizations, species, planets, and even stars exist for durations that are brief compared with the full chronology of the universe. Yet every one of those scales is part of the same continuous story. The atoms within living organisms were produced by ancient stars. Those stars formed within galaxies assembled from primordial matter. The matter itself originated in conditions established shortly after the beginning of cosmic expansion. Across all scales, the narrative remains connected. As we arrive at the deepest future, the pace of change has become extraordinarily slow. The universe no longer contains bright stars crossing the sky or galaxies filled with active regions of star formation. Instead, the remaining particles drift through expanding space. Radiation stretches to ever longer wavelengths. Energy becomes increasingly uniform. Thermodynamic differences fade. The cosmos settles into a condition that is stable not because motion has ceased, but because opportunities for large-scale transformation have become exceedingly rare. There is a certain scientific simplicity in this final state. No dramatic events are required. No sudden ending arrives. The future unfolds through gradual processes operating over unimaginable intervals. Entropy increases. Energy disperses. Structures dissolve. The universe becomes quieter not through interruption, but through continuity. The same laws that produced complexity also guide its eventual decline. In that sense, the final equilibrium of the cosmos is not separate from its beginning. It is one part of a single physical progression extending across all of time. If you imagine that distant future now, there is no need to picture emptiness as something unsettling. From a thermodynamic perspective, equilibrium is simply a condition in which change has become minimal and energy is distributed as evenly as possible. The universe is not struggling against this state. It arrives there naturally. Every process contributes a small part. Every era moves gradually toward it. Across immense spans of time, the cosmos settles into balance. And as our own journey through this chronology comes to an end, you can allow the scale of these timescales to recede into the background. The first stars, the galaxies, the black holes, and the deep future all belong to the same universe, yet they unfold across durations so vast that there is no urgency within them. The cosmos has taken billions, trillions, and far greater spans of years to evolve. Nothing within this story moves quickly when viewed from the perspective of eternity. For now, there is only the quiet understanding that the universe continues according to its laws. Space expands. Particles drift. Quantum fields remain. The future extends onward. Equilibrium approaches. The immense chronology we have followed settles into stillness, not through force, but through the patient operation of physics across time beyond measure. Thank you for traveling through the history and future of the universe with Universe Scientist Stories. As the scales of cosmic time grow larger and quieter, you can leave them behind and return your attention to the present moment. The stars, the galaxies, the black holes, and the distant future will continue their paths whether we think about them or not. There is nothing left to calculate and nowhere else to travel tonight. The universe is vast. Its history is long. Its future is longer still. Yet at this moment, you are here, safe, resting, and separate from those immense spans of time. The processes we have discussed unfold across durations so great that they place no demands upon the present. They simply exist as part of the larger story of reality. So allow the chronology to become quiet. Allow the scales of years, trillions of years, and unimaginable future ages to fade into the background. Let the final equilibrium of the cosmos serve as a reminder of stillness. The universe eventually reaches a state in which nothing significant remains to disturb its balance. Everything settles. Everything becomes calm. Everything approaches rest. And with that final image of a universe at new perfect equilibrium, expanding gently through an endless future, our journey reaches its conclusion. May your thoughts become lighter, your breathing slower, and your rest undisturbed. Have a peaceful night and sleep well.